Hello, this is video number 13 on my single variable calculus 2. In this video, we're going to go over integration by parts. Integration by parts is an analog of product rule in differentiation. So if you write down the product rule, which is uv prime equals uv prime plus vu prime, and integrate both sides, integral of uv prime by the fundamental theorem of calculus becomes uv. An integral of this side, we can break it up into two integrals. One of them is integral of uv prime dx, and the other one is integral of vu prime dx. Now, if you replace v prime dx by dv and u prime dx by du and bring one of them to the other side, you'll get this formula. Integral of u dv, so this one is equal to uv minus integral of v du. So for the rest of this video, we're going to go over some examples. Here is the first example. We want to evaluate integral of x e to the power of x dx. So in order to make this simpler, we want to choose one part to be u, and note that when we take u as one part of the integrand, then we'll differentiate that. So which part of this integrand can be differentiated and makes it easier? Well, is it going to be x or is it going to be e to the power of x? If you differentiate x, you get 1, which is simpler. But if you differentiate e to the x, that doesn't really change anything. So we're going to choose u to be x and dv to be e to the x dx. That gives us du equals dx and v equals e to the x. Then we can go ahead and evaluate this using the integration by parts. So this is uv x e to the x minus integral of v, which is e to the x, times du, which is dx. And now we know how to integrate e to the power of x. So this is going to be x e to the x minus e to the x plus c. So this would be the answer to the first part of this problem. So let's look at the second part of this problem. In this integral, we want to evaluate the integral of x squared sine of x. If we differentiate x squared, we get something simpler. We get 2x. And then we can differentiate again and we get a constant. But if we differentiate sine of x, we don't really get anything simpler. We get cosine of x. And if we differentiate again, it goes back to negative sine of x. So it makes sense to choose u to be x squared. So let's take u to be x squared and dv to be sine of x dx. We are going to differentiate u. We get du equals 2x dx. And we're going to integrate sine. We get negative cosine of x. Now we can write down the integral from 0 to pi x squared sine of x dx, which was the initial integral that they gave us, and apply integration by parts. So this would be u x squared times v negative cosine of x. But notice that this is a definite integral. So we have to evaluate this from 0 to pi minus integral from 0 to pi v du, which is negative cosine of x times du, which is 2x dx. Okay, so let's substitute pi and 0 to see what we get. We get pi squared negative cosine of pi minus, well, when we plug in 0, we get 0 squared negative cosine of 0, which is just 0. And then we have a negative sign here. We also have a negative sign here, so that becomes positive. Positive integral from 0 to pi cosine of x times 2x dx. And I can take this 2 out to make things a little bit simpler. And then we can go ahead and evaluate this integral. So how do we evaluate this integral? We can do something similar. Again, if you differentiate x, you can make things simpler. So let's take u equals x, dv equals cosine of x dx. So that tells us du equals dx and v equals sine of x. So let's see what happens here. We have sine of pi, which is negative 1, times negative 1, that's positive 1, times pi squared, that gives us pi squared. This whole thing becomes 0. And then we have plus 2. Well, now we're applying the integration by parts again. So uv, that is x times sine of x from 0 to pi minus integral of v du. V is sine of x, du is dx. Let's now plug in the values, and again this is from 0 to pi. This is pi squared plus 2 parentheses. When we plug in pi, we get pi sine of pi minus 0 sine of 0 minus integral of sine is negative cosine, so this becomes positive from 0 to pi. So this is equal to pi squared plus 2 parentheses. Okay, so sine of pi is 0, and this is of course 0 as well. So we can plug in cosine of pi here. We have minus cosine of 0. So this gives us pi squared times 2. Cosine of pi is negative 1. Cosine of 0 is 1. So that becomes plus 2 times negative 1 minus 1, which is pi squared minus 4. So that is the answer to this problem. So let's look at the next part of this problem. So the next part is integral of natural log of x. So integral from 1 to e of natural log of x dx. We need to take u as part of this integral that is easily differentiable and v as part that is easily integrable. So there's like just really one part here. We have natural log of x. So that's the natural choice for u. So u equals natural log of x, and the remaining part is dv. So if we integrate dv and differentiate u, we get 1 over x dx for du, and for v we get x. So we can write natural log of x times x from 1 to e minus integral from 1 to e of v du, which is x 1 over x dx. Let's plug in e in there. We get natural log of e times e minus natural log of 1 times 1 minus integral from 1 to e of 1 dx. Well, natural log of e is 1. Natural log of 1 is 0. So this whole thing becomes e. And then minus natural log integral of 1 is x from 1 to e. So this is going to be e minus 1, which is e minus e plus 1. So the answer to this part of the problem is 1. Let's look at one more example. Okay, so we have integral of e to the power of x sine of x. So we can take really either one of these two as u or dv. The reason is derivative of e to the power of x is e to the power of x. Derivative of sine of x is cosine of x. So they aren't really changing all that much. So we can take u to be e to the x, dv to be sine of x dx. We are going to differentiate u. We get du is e to the x dx. Integrate sine. We get negative cosine. Now we can apply the integration by parts. So u, which is e to the x, times negative cosine of x. So this is uv minus integral of v du, which is negative cosine of x, e to the power of x dx. And this is the integral that we started with. We started with integral of e to the x sine of x dx. So unfortunately, it didn't really change all that much. It became something of similar difficulty. So we have negative e to the power of x cosine of x. I'm going to multiply the positive negative signs. I get a positive sign, and I get e to the power of x cosine of x dx. So what can we do? Well, we can repeat the same process and go back to e to the power of x sine x. Let's do that. But we're going to have to choose u and v to be the same type. So u equals e to the power of x. dv is going to be cosine of x dx. du is e to the power of x dx. And v would be sine of x. So we're going to go ahead and use integration by parts. So negative e to the power of x cosine of x uv, which is e to the power of x sine x, minus integral of v du, which is sine x e to the power of x dx. Now let's see what we got. We started with integral of e to the power of x sine x, and we ended up with negative the same thing plus something else. So that tells us that if I take twice the integral of e to the power of x sine x dx, so what I did was I took this guy and I moved it to the other side of the equality. So I got twice that integral is equal to negative e to the power of x cosine of x plus e to the power of x sine of x. And of course, we always need a plus c. So we're going to divide by 2, and that would be our final answer. So anytime you're dealing with exponential times sine, exponential times cosine, you'd have to do integration by parts twice, and then you'll bring the same integral to the other side and divide both sides by 2. Okay, so we'll do a few more examples on this. Evaluate each integral. So similar to before, integrating tan inverse is the objective of the problem. So we really don't have a lot of choices. The only choice is really just to take u equals tan inverse of x and dv equals dx. So derivative of u is 1 over 1 plus x squared, and v is just x. So the integral is going to be uv, which is tan inverse of x times x minus integral of v du, which is x 1 over 1 plus x squared dx. Now, how do we integrate this? If you look at this one, you notice that the derivative of this one is right here. So it makes sense to do a u substitution for u equals 1 plus x squared, and that gives us du is 2x dx. So that means x dx is 1/2 du. So this would be, I'm going to put the x in front, x tan inverse of x minus integral. At the bottom I have u, and then x dx is 1/2 du. And we know what this is. That is just natural log. So this is x tan inverse of x minus 1/2 natural log of absolute value of u, and then plus c. Now we're going to have to plug in u back and see what we get. So u is 1 plus x squared, so we have to plug that back here. Now 1 plus x squared is always positive, so we don't need the absolute value. We get x tan inverse of x minus 1/2 natural log of 1 plus x squared plus c. Okay, let's look at the next part of this problem. So the next part is x secant squared of x. So again, if we differentiate x, then we would be able to get something simpler. So for this, we're going to take u equals x, dv equals secant squared of x dx. So we know that derivative of u is just 1, so that's just dx. And we know that integral of secant squared is tan of x. And that is exactly what I had. So let's see, we get uv, which is x tan of x, minus integral of v, which is tan of x, du, which is x, which is dx. Okay, so now, how do we evaluate the integral of tangent? We can turn that into sine and cosine. So this is x tan of x minus integral sine of x over cosine of x. Now, derivative of cosine is negative sign, which is on top. So we can use a u substitution. U equals cosine of x, du becomes negative sine of x dx. So in other words, negative sine x dx is exactly du. So this is going to be equal to x tan of x minus or plus integral du over u, which is x tan of x plus natural log of absolute value of u plus c. So plugging that back into here, we get x tan of x plus natural log of absolute value of cosine of x plus c. So that is our final answer. Okay, next one. And then I'll summarize and give you some ideas of what to choose for u. So we want to integrate natural log of x squared. Okay, so integral of natural log of x squared from 1 to e. Well, for the same reason that we talked about earlier, we should use u as natural log of x squared, because then it is easy to differentiate this. So dv would be dx, u becomes 2 natural log of x, and then times 1 over x, and v is going to be x. Well, we can apply the integration by parts again. So uv, so that's natural log of x squared times x, that is from 1 to e, minus integral v du, which is 2 natural log of x over x dx. And the limits are the same limits. Notice that we're not doing any u substitution. That's why the limits of integration do not change. Let's plug in e. We get natural log of e squared times e. Plug in 1. We get natural log of 1 squared times 1 minus twice integral from 1 to e of natural log of x dx. So natural log of e is 1. Natural log of 1 is 0. So this would be just e minus 2. And then this is an integral that we evaluated earlier in the video. So that's just times 1. So the answer is e minus 2. Now here are some tips as to how to choose our u and dv. The most common integrals that you'll see in this class are going to involve products of polynomials, natural log, inverse trigonometric functions, and exponentials. We typically use u as the natural log if you have natural log. If not, choose inverse trig. If not, choose the polynomial. To summarize, we talked about integration by parts. Integral of u dv is uv minus integral of v du. To use integration by parts, set u part of the integrand whose derivative is simpler than itself. Set dv the remaining portion. Differentiate u to get du. Integrate dv to get v, and then you plug it into the formula of integration by parts. Now sometimes you have to apply this process a couple of times. The best choice of u in order is typically logarithms, then inverse functions, trigonometric functions, and then polynomials. And note that sometimes if you don't know what you should do, you're gonna have to try something and see if that works. So staring at a problem and doing nothing will never solve a problem. That brings me to the end of this video. I will see you in the next video.